Dear students, today we will talk about brillioun zones. Correct the spellings of your own. So we are talking about brillioun zones. So for that you first need to know about the wave vector. I hope all of you are aware that this quantity k, which is a vector quantity, is denoted by 2 pi by lambda. Now how do you realize this kind of a vector? 2 pi is a full phase difference that you can imagine. Full phase, and lambda is the total wavelength. So a ratio of the total phase to total wavelength or path difference is denoted by this wave vector k, 2 pi by lambda. Now when you deal with the same quantity in a lattice, in a solid, right, we know that these atoms are arranged in all possible directions. You can imagine at least a 3 dimension, right? So this k can be modified and written as n pi by a, where this lambda goes to a. A is the side of the solid, length of the side, and this 2 gets replaced by n, because we know that 2 pi is generally the angle in the plane, right? 2 pi is the angle in the plane, but once we are dealing with 3D, we have to replace this 2 by n. Now if you can imagine line segments whose lengths are of pi by a integer, then the zones enclosed by such lines are called as brillioun zones. Brillioun zones. I'm again repeating that since k is 2 pi by lambda, in case of a solid, this pi will go to a, where a is the length of the side of the solid, right? This 2 will go to n because now we are not dealing with 2 dimension but more than that. So this k will be represented as n pi by a, right? Now if we imagine line segments whose lengths are of order pi by a, then any regions in the solid which are enclosed by these line segments are called as brillioun zones. Now the question is, how do we geometrically conceive this idea? For example, consider a monoatomic lattice in which the atoms are arranged in a one-dimensional mode. Okay, this is for simplicity to understand how we begin with. Now these are the atoms which are arranged in the plane of the solid. Initially you need to have the concept of Wigner Shear cell. You might have found it in books. Now let us today get an idea of what this Wigner Shear cell is all about. So what does it say? If you choose randomly any point at the center and we connect it to all the points that it can find in its vicinity, for example this point, right, then the idea is we need to find a region in space in which all the neighboring points are more close to the given point than to any other point. A region in space in which all the neighboring atoms are more close or found more close to the given point, to the chosen point, than any other point. So what do we do for that? We draw perpendicular bisectors to all such lines. Perpendicular bisector to this will be like this, for this it will be like this, for this it will be like this, for it. And then we keep on drawing these perpendicular bisectors, and we find that these perpendicular bisectors enclose certain region. This is the region in the vicinity of which, within the fold of which, all other neighboring atoms are more close to the given atom than to any other atom. And this kind of cell is called as Wigner Shear cell. Now if you have to imagine a brillioun zone, you choose the lines like this. Initially we can go back to the original this description, that is k was equal to 2 pi by lambda, but then we had modifiedly written this k as equal to n pi by a. In case of a solid, if we equate these two, we find that 2 pi by lambda is equal to n pi by a. Pi and pi will go. We are left with 2a is equal to n lambda. I hope all of you can easily identify it with Bragg's law, where we have actually 2d sine theta is equal to n lambda. Here sine theta is 1 because theta might be 90. So how do we conceive that idea? For example, Again, we choose an arrangement of atoms which we had chosen previously, right? And choose a point at the center and connect it to all the neighboring points. Then, for the case of brillioun zones, we will choose only such lines which are perpendicular to each other, because the relation comes out to be 2a is equal to n lambda. This can be true only if sine theta is equal to 1, and which can be further true only if theta is 90. So we choose subsequent lines only at an angle of 90. If we have initially begun to choose this line, we draw perpendicular. Next we draw perpendicular to this line and not this line, not adjacent line, but the line which is at an angle of 90. So we draw perpendicular to this, then a perpendicular to this, then a perpendicular to this. This region which has been enclosed is the first brillioun zone. It's the first brillioun zone. Now we can choose a second orientation of lines as well. Now we can choose this line. Its perpendicular bisector will be like this. Then this line, its perpendicular bisector will be like this. Then this line, its perpendicular bisector will be like this. And then this line, its perpendicular bisector will be like this. Now you can find that there are 4 such areas which get traced or enclosed outside the first brillioun zone. These are the second brillioun zones. So these are this or this. These are called as second brillioun zones, right? So for first brillioun zone, you can choose to write that k goes from plus minus pi by a, kx. Now we have to choose 2 directions. Imagine we have drawn the atoms in a plane. So we'll choose only kx and ky vector. Kx will go from plus minus pi by a and ky will also go from plus minus pi by a, right? For the second brillioun zone, kx will go from plus minus 2 pi by a and ky will also go from plus minus 2 pi by a, right? So you can imagine this point as minus pi by a, this as plus pi by a, this as minus 2 pi by a, and this point as plus 2 pi by a. So these regions that are enclosed in the successive, these lines, Bragg's lines, these lines are called as Bragg's lines, are called as brillioun zones. I hope that gives a very fundamental and preliminary idea of what brillioun zones are all about.